Okay, this lesson is called Linear Approximations. It's section 2.9, and it is a section where we're going to use lines, specifically tangent lines, to approximate values of a curve. And we'll get into some applications at some point. I might save those for class. So pause this if you need to read what's here. But what I basically want you to do is graph a curve and its tangent line. So I came up with an example for you. If you want to graph the curve x cubed minus 4x squared plus 2x minus 1, I guess I could write that down, and then graph a tangent line to it. So again, let's see, x cubed minus 4x squared plus 2x minus 1, and then for your y2, try 2x minus 1. So that's a curve and its tangent line. Now zoom in on those two graphs repeatedly, again and again and again. Zoom box or zoom in, okay, and make sure that you're honing in on the point 0, -1, because that's where this is tangent to this curve. And then what do you notice? So what we're going to do, it's illustrated on the next slide, is we're going to use points on the tangent line, which are really, really close to points on the curve, to approximate them. Okay, so this is sometimes called a linearization, again, a linear approximation, or a tangent line approximation of a function at some number a. Okay, so take a look at this graph. In a linear approximation, and I'm just reading for now, we use the tangent line at some x value, and we'll call that x value a, to approximate the y value at that same x value, or at a, on the curve. Now, at some different x value close to this one, L of x, which is on the line, will be very close to the value of f of x, and hence is our approximation. So I'm going to zoom in on this now, so you can see it illustrated here. Okay, so let me point some things out. So here is, here's the x value, probably 3, right, is where we want the tangent, is where we're going to draw a tangent line. And when we draw the tangent line, if I'm concentrating on 2.5 or 2.6 and I want to know the value on the curve, the y value on the curve at 2.6, I can use the y value from the tangent line at 2.6. And it's really, really close to being the y value that I want. So I'm using this y value to approximate this y value. Okay? So this is x, this is x. I'm sorry, I guess I should be pointing to this. These x's are the same, right? Because they're at the same place as far as your x-axis goes. But the y values are really close. This y value is going to be a little bit lower than the one that we're looking for. And we're using the point of tangency right here to find that. Okay, so in this version of the picture, if you noticed, I've spaced it out a little bit more, so it's a little bit easier to see, even though the picture is smaller now. But I'm labeling the points the same. So this is a, f of a. This is where I'm drawing a tangent line. And I'm going to use the y value over here at this particular x to approximate this y value at the same x. So I'm going to start out with point-slope equation, or the point-slope form of the equation of a line. And let's now figure out, okay, how's this going to work? Well, I want my... I'm looking to solve for this because this is my answer for my approximation. So I want L of x to be one of the y values, and now I'm on a line, so I know my other y value has to be here, and then here's x, and here's another x value, and then you know your slope of a tangent line, right? Okay, so again, the first y is going to be L of x, right? That's our first y value. The next y is going to be, and I wish I could do these things at the same time. So this was our first y value, this is our second y value. So now we have minus f of a, and then equals the slope. How do you find the slope of a tangent line? Pause, pause, pause. Right, you get its derivative, right? So we need the derivative at a, that's the slope, times x minus x. Now make sure that your x values match these x values in the proper order. So in parentheses we then have x minus a. Okay? Alright, now let's look at, again, what we want to get by itself. What we want to get by itself is this. So all I'm going to do is move the f of a over, right? So your L of x, which approximately equals f of x, your L of x equals f of a plus f prime of a times x minus a. And that's where it comes from. So again, it's just from the point slope form of a line. You can very, very easily derive what's called a linearization, which is a really important AP topic. Okay, so let's do one. We want to, and this is an example from the book, so feel free to open the book and read the directions. But what number 6 is asking you is to approximate 0.9 cubed, right? So I want to know what is f of 0.9 if this is my f of x. So first I need to know different pieces of this formula. And in the end I'm going to solve for f of 0.9 by approximating it with the value of the tangent line of 0.9. So the biggest amount of work that you're going to have to do is to find this derivative. So let's start. F prime of 1 is the limit. Which one do I think is going to be easier? I think as x approaches 1 is going to be easier for me. And I'm going to go f of x minus f of 1 over x minus 1. Now I know the top is just x cubed minus 1, which is the difference of two cubes, right? And oops, I forgot my limit, so let me squeeze it in here. So for the difference of two cubes, I take the cube root, I keep the same sign, I take the cube root, and then I have the first term squared. This sign's always opposite. The product of those two terms, and then this is always a plus, and that's the last term squared. So how did that help? It helped because now we can cancel things, right? And now we can actually take the limit as x approaches 1, and we can get 1 squared plus 1 plus 1, or 3. So our slope is 3. Now we're going to plug that in for f prime of a, right? Because that was f prime of 1. So in this case, a is 1. Oh, and I guess I probably should have pointed out, why are we getting f prime of 1? Well, because if we're trying to estimate f of 0.9, you saw graphically that this has to be really close to some other number for the tangent line y value to be kind of close to the curve's y value. So what's close to 0.9? 1. So that's why we used a 1. All right, so this approximately, or approximates L of 0.9, which is f of 1, again that's our a, plus f prime of 1 times x minus 1. Okay, so this is x, this is x, this is x, and all the other ones are your a's. A. Okay, so let's see, f of 1. Here's your function, right? F of 1 is 1 cubed. F prime of 1, we found. 0.9 minus 1 is negative a tenth. So that's 1 minus 0.3, or 0.7. Now I will leave it up to you to compare that to what the actual value of 0.9 cubed is, but it's going to be gosh darn close. Okay, so that's all the further we'll go for the video. Here's some homework you can start on, and we'll look at some applications of these in class.